Welcome! Today we're going to do linear independence and basis. So starting with linear independence, we first need to consider linear dependence. Let U be a set of vectors, U1, U2, up to UN, in a vector space V over a field K. Then the vectors Uj, these vectors, are linearly dependent. It says dependent if there exist scalars a1, a2 up to an that are not all zero, such that a1 u1 plus a2 u2 plus etc plus an un is equal to the zero vector. If U is not linearly dependent, then U is linearly independent. Okay, definition 17. Let U be a collection of vectors in the vector space V over the field K. Then the vectors lowercase u subscript j in here are linearly independent if whenever you have this equation equals the zero vector, notice that zero is bold, then we must have all of these scalars equal to zero. Okay, if we have a set S of m vectors in the vector space V, and if the zero vector is in it, then S is linearly dependent. And the reason why is because let's suppose that one of these vectors here is the zero vector. Let's suppose it's Vj, V subscript j, somewhere in there. Then when we set up this equation, notice that 0 times V1 plus 0 times V2 and so on plus 1 times the one that was 0, the one that was the zero vector, plus 0 times all of the other vectors added together. This gives us the zero vector, but not all of the scalars had to be 0. The coefficient of that vector that is 0 could be 1. All right? And so when we have this, we're not forced to have all coefficients 0. So therefore, if 0 is in the set, then that set necessarily has to be linearly dependent. Okay, remark 10.2. Let S be the set containing just the one vector V in the vector space uppercase V, then that's linearly independent. Okay, so let's see why. Clearly, if the scalar k times v is the zero vector, then k is 0 since v is not the zero vector. And conversely, the other way holds. So in other words, kv is the zero vector if and only if k is equal to 0. Okay, remark 10.3. Let S be the set of m vectors in the vector space V, and suppose that Vi is equal to k times Vj for some vectors such that I is not equal to j and k is in the field of scalars. In other words, one of these is a multiple of another. Then S is linearly dependent. Right, and so if you set up this equation here, so a1 v1 plus a2 v2 etc. up to say vi, and then you have etc., and then you have a j vj etc., and then you have a mvm, equals the 0 vector. So when you have this, and now we take that vi and replace it with k times vj. Okay, so then we have the same thing, a1, v1, etc. And then when we get to vj, since we have replaced vi with k vj, we get k plus aj vj, etc. am vm is the 0 vector. It will be possible to have the coefficients not all 0. Okay, let's move on to the next page. Let S be the set containing two vectors. They're non-zero vectors in the vector space V. S is linearly dependent if and only if there exists a non-zero scalar k such that v1 is equal to k times v2. In other words, v2 is a multiple of v1. Okay, so the way we want to think about this, first assume that v1 is k times v2. Well, if that's the case, then v1, or 1 times v1 minus k times v2 is equal to the 0 vector. And since 1 and minus k are not all 0, we see that S is linearly dependent. Okay, now conversely, suppose S, which is v1 and v2, is linearly dependent. Well, if that's the case, then there exist scalars a and b. Again, this is usually the real numbers, such that a v1 plus b v2 is the 0 vector with a1 and a2 not both 0. Okay, so if they're not both 0, then we can divide by one of them. I'm out of space here, but so divide by 1, and then without any loss of generality, assume that a, actually that should say b, right? So a and b. Without any loss of generality, assume that a is non-zero. So w log, without any loss of generality, assume a is not equal to 0. So if it's not 0, then you can divide by it. Divide and get v1 is equal to minus b over a times v2. And so this minus b over a is our k, and so we get the required result. And so that holds true in both directions, if and only if. Okay, example 10.1. Let S1 be the set of vectors 1, 1, and 2, 2, and S2 be the set of vectors 1, 1, and 2, 3. Show that S1 is linearly dependent while S2 is linearly independent. Okay, now following from the theorem or the remark above, so let's say by remark 10.4, since the vector 2, 2 is 2 times the vector 1, 1, S1 is linearly dependent, right? Okay, but there's another way of viewing this. So let's say alternatively, suppose a times 1, 1 plus b times 2, 2 is equal to the 0 vector, 0, 0. Now we can write this in a matrix way. Then we've got the matrix 1, 2, 1, 2 times AB is the 0 vector. Okay, now what happens when we try to solve this system for A and B? Well, this matrix uppercase A here is not invertible, so we will have to parameterize our solutions. All right, so let's have a look at this via row reduction. So the augmented matrix, or this matrix 1, 2, 0, 1, 2, 0, has row reduced echelon form 1, 2, 0, 0, 0, 0. And so that tells you then that you can write B in terms of A and parameterize the solution to this equation. All right, so let's do that. So we have A plus 2B is 0, so A is equal to minus 2B, and B is equal to B. Hence, AB is equal to minus 2, 1 times a parameter t, where t is any real number. Okay, so what I've done here is calculated a basis for the null space of this matrix right here. All right, but we will get to those concepts soon enough. Okay, and so this shows you that these two vectors here are linearly dependent, because the A and B, they're not both 0 here. So A and B, not always both 0, right? So I can choose a t that's, say, t equals 1, for example. All right, so a lot on that one. Now let's have a look at this. So for S2, suppose that we have alpha times 1, 1 plus beta times 2, 3 equal to the 0 vector. Well, if that's the case, then we can write this as a matrix equation. 1, 2, 1, 3 times alpha beta is the 0 vector, but this matrix uppercase A right here is invertible. So let's just say we must have alpha equals 0 and beta equals 0 since A inverse exists. And by uppercase A, I mean this matrix 1, 2, 1, 3. So let's write that in the little space that we have, 1, 2, 1, 3. Okay, great. Let's move on to remark 10.5. Let S consist of M vectors in a vector space V, and suppose W is a subset of that set S. Then W is linearly independent. Okay, so let's suppose then that W is equal to, without loss of generality, let's suppose, because we can always shuffle it around, right? Let's suppose that it's the first n vectors. Where n is less than or equal to m. Right? So that would make this a subset, and a proper subset if n is strictly less than m. Could be the same, of course. Okay, so we have a subset of S. Whoops, other way around. W is a subset of S. All right, so we've got to show that W is linearly independent following from the linear independence of S. So what we want to do is set up our equation. Suppose, here I'll say, and suppose A1 V1 plus A2 V2 and so on up to AN Vn, and I should put tildes under all these because I'm writing them by hand. Suppose this adds up to the 0 vector. Okay, then if we have A1 V1 plus A2 V2, etc., plus AN Vn, put a bracket around that because we're talking about this, plus a n plus 1, Vn plus 1, and so on up to AM Vm equals 0. And incidentally, so what I'm doing here is I'm going to set up a proof by contradiction, right? So we'll add to this statement up here at suppose while A1, A2, etc. up to AN are not all 0. Okay, so in other words, I am assuming that W is linearly dependent in this assumption, and I'm going to seek out a contradiction here. So if these are not all 0, but S is linearly independent, so whenever you set this up, all of these have to be 0, right? That's your contradiction right there, because some of these are not necessarily 0, right? And so when we have this equation, So we'll say but we have the AJ not all 0 here, which is a contradiction. Of the assumption that the set S is linearly independent. Okay, so therefore the opposite of this assumption right here must be true. In other words, W is linearly independent. So W must be linearly independent. Okay, let's move on to the next page. Where we have some examples, which I'm sure you're finding refreshing at this point. Right? Let U, V, and W be 3 vectors in 3 space. Show that U, V, and W are linearly dependent. All right, so let's suppose alpha, beta, gamma are 3 real numbers such that alpha U plus beta V plus gamma W is the 0 vector. Okay, then what we can do is set up a matrix equation for this. It looks like this. 495 times alpha, beta, gamma is the 0 vector. Okay, so what happens when we try to solve this, right? Are we forced to have all zeros? Or can the alpha, beta, gamma be not all 0? Okay, so let's take a determinant of this matrix. We can do row reduction, or we can just take a determinant of this matrix. So the determinant of this matrix right here is 1 times 3925 minus 1 times 1905 plus 4 times 1302, and this simplifies as, see, 15 minus 18, and then minus 5 minus 0, and then plus 4 times 2 minus 0, which simplifies as minus 3 minus 5 plus 8. That simplifies to 0, doesn't it? 8 minus 8 is 0. Okay, good. So our determinant is 0. So what that means then is if we try to solve this, we're not going to get alpha, beta, gamma equal to 0, because if the inverse existed, we could just multiply by it on both sides here, and the inverse of the matrix times the 0 vector would give us the 0 vector. So that's what would happen if the determinant were not equal to 0. But since it is equal to 0, we are able to find alpha, beta, gamma not all 0, such that this equation is satisfied, which is equivalent to this equation. Let's write that over here, and then I'll maybe do a row reduction there. So there exists alpha, beta, gamma not all 0 such that alpha u plus beta v plus gamma w is the zero vector. Okay, in other words, those three vectors are linearly dependent. Now, I'll get on the computer and I'll type in that matrix. So we have 1, 1, 4, 1, 3, 9, 0, 2, 5, and then for good measure I will put in the column of zeros here as well on the right. Okay, so in other words, I've just written the augmented matrix. So let's display that. Okay, so there it is. You can see it matches this. And now what I want to do is find the row reduced echelon form quickly. And then display that as matrix 2. Okay, so let's say that here in this little space, the matrix 1, 1, 4, 0, 1, 3, 9, 0, 0, 2, 5, 0, row reduces to 1, 0, 3 over 2, 0, 0, 1, 5 over 2, 0, and 0, 0, 0, 0. So you can see that the row reduced echelon form there has a row of zeros, right? Which tells you that matrix is not invertible. Okay, but also it tells you another thing. It tells you how to talk about the set of solutions to a uppercase X equals 0 vector, right? So let's have a look and unpack that. So what this says then is that alpha plus 3/2 gamma is 0 from the first one, or row, and beta plus 5 over 2 gamma is 0. And so we can write alpha, beta, gamma in terms of just gamma. So we've got minus 3 over 2, minus 5 over 2, and 1 times gamma. So if I choose any real gamma, I get an element of what is called the null space of the matrix A. In other words, I get a solution to uppercase A, X equals 0 vector. All right, and so if you choose, say, gamma is equal to 2, then you'll get alpha is minus 3, beta is minus 5, and gamma is 2. That tell you that these three vectors are linearly dependent because those numbers I just spoke are not all 0. Okay, example 10.3. Suppose we have these three vectors u, v, and w in 3 space. Show that they are linearly independent. Okay, so we'll set up the same equation. Suppose alpha u plus beta v plus gamma w is the 0 vector. Well, what this says then is that 1, 2, 3, 2, 5, 7, 1, 3, 5 times alpha, beta, gamma is the 0 vector. Okay, so one way to quickly decide is to take the determinant. So if we take, given that it's a square matrix, that's doable, right? So taking the determinant of this matrix, if it's non-zero, then the inverse of that matrix exists, and we can multiply it, and we would obtain then alpha, beta, gamma is the 0 vector, right? So let's do that. Determinant of this matrix is equal to 1 times 5375 minus 2 times 2335 and plus 1 times 2, 5, 3, 7. Okay, so we have 25 minus 21 minus 2 times 10 minus 9 plus 1 times 14 minus 15. Okay, let's simplify this. So here we have 4 minus 2 minus 1, which is 4 minus 3 is 1, and that is non-zero. So what that says is that the matrix A, okay, so let's call this A, alpha, beta, gamma over here. So we identify that this is A. So A inverse exists, and hence alpha, beta, gamma is A inverse A times alpha, beta, gamma, which is A inverse times the 0 vector, which of course is the 0 vector. And so what we've learned, alpha is beta is gamma, which is 0, so linearly independent. That set S is linearly independent. Okay, moving on. Remark 10.6. Any two vectors in 3 space are linearly dependent if and only if they lie on the same line through the origin. So let's draw a quick picture. Even though that's 3 space and I'm drawing on a plane. Okay, suppose this is U, and then this is V to here. Okay, so these are linearly dependent when they're on the same line, as in the vectors U and V are parallel, so I can line them up on the same line through the origin. Any 3 vectors in 3 space are linearly dependent if and only if they lie on the same plane through the origin. So, example, if we have this, then I can get U as a linear combination of V and W here if they are on the same plane. All right, so I'll pick this page up and make a plane out of it. You should do that too. And so if you have 3 vectors that are parallel to a given plane, then they must necessarily be linearly dependent. Okay, let's move on to the topic of basis of a vector space. Definition 18. A matrix is in row reduced echelon form if the following 4 conditions hold. All rows, if any, consisting entirely of zeros, so if any rows consisting entirely of zeros, in other words, appear at the bottom of the matrix. So whenever we have a row of zeros, it has to be at the bottom of the matrix. The first non-zero number starting from the left in any row not consisting of entirely zeros is a 1. 2 successive rows do not consist, if 2 successive rows do not consist entirely of zeros, then the first one in the lower row occurs farther to the right than the first one in the higher row. So in other words, we've got something like this, and then the row below that has to have its pivot farther to the right. Okay? Any column containing the first one in a row has zeros everywhere else. So that's columns, right? Okay, so if this is a pivot, then I need to have zeros everywhere else in that column. If only conditions 1, 2, and 3 hold them, then the matrix is in row echelon form. Okay, as opposed to row reduced echelon form. So what we're generally going to do to answer questions is put our matrix in row reduced echelon form. So all, as in the entire Gauss-Jordan algorithm. Okay, next page. For example, the matrices, the identity, this matrix, this one, all of these matrices are in row reduced echelon form. So let's have a look at where our pivots are. Pivot there, pivot there, pivot there. We do not have a row of zeros in this matrix, but the first non-zero entry in each row appear farther to the right than the previous one. And we have zeros in the column everywhere else. Same for this. Now let's have a look at this one. So the pivots are farther to the right. We have zeros everywhere else where there are pivots in a given column. And it does not matter that the numbers in this final column are not 1 or 0, because we have exactly 3 rows and exactly 3 pivots. So it doesn't matter what's here. All right, so this particular matrix is only in row echelon form, not row reduced echelon form, because our leading pivots don't have zeros above them. Okay, theorem 26. The non-zero rows of a matrix that is in row reduced echelon form are linearly independent. So we're talking about rows here, right? So these 3 are linearly independent. So let's write that example. This set 1, 0, 0, 3, 0, 1, 0, 2, 0, 0, 1, 2 is linearly independent. So taking the row reduced echelon form of a matrix is a good way to get a set of vectors that are linearly independent. You just throw away the rows of zeros and what remains, if it's in row reduced echelon form, is a set of linearly independent vectors. Okay, definition 20. Let B equal to u1, u2 up to un be a set of vectors in a vector space V over K. Then B is called a basis of V if both of these following 2 conditions hold. The span of B is V. Now remember, that means that I can obtain every vector in the vector space V as a linear combination of these vectors. And condition 2, the vectors in B are linearly independent. Okay, so they have to have those 2 properties. I have to be able to get every vector in the vector space V as a linear combination of those vectors, and those vectors have to be linearly independent. For example, if we're talking about 3 space, then the vector 1, 0, 0, 0, 1, 0, and the vector 0, 0, 1, these are 3 linearly independent vectors in 3 space, and I can get every vector as a linear combination of those 3 vectors. So let's write here, e.g. E1 equals 1, 0, 0, E2 equals 0, 1, 0, and E3 equals 0, 0, 1. So E1 E2, E3 is a basis for R3. Okay. A basis of a vector space V is not unique in general, and there may be exceptions for unusual fields of scalars, like, for example, integers modulo 2, right? So this is an unusual field of scalars. Okay, suppose we have a B, U1, U2 up to UN. Suppose this is a basis for the vector space V. Then for all V in the vector space V, there is a unique ordered n-tuple of scalars A1, A2, dot, 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 up to AN, such that this sum of linear combinations of these basis vectors gives us V. All right, so in other words, we can always write V as a unique linear combination of the elements in B, in the basis. Okay. Theorem 28, if B1 and B2 are two bases for a vector space V, then they have to have the same number of elements. The dimension of a vector space V, so what this says is that that number of elements is an invariant of that vector space V. It's the same for every basis that you have of that vector space V. Okay, so the dimension is that invariant. The dimension of a vector space V, denoted dim of V, is the number of elements in any basis of V if this number is finite. So there are some vector spaces that do not have a finite dimension. Okay, the trivial vector space, the vector space just containing the zero vector, is defined to have dimension 0. Definition 22. If B is the set of vectors U1, U2, dot, 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 up to UN, if this is a basis of the vector space V, then B is an orthogonal basis of V if for all Ui and Uj in B with I not equal to j, the dot product is the zero scalar, right? Remember, the dot product is a scalar. Okay, definition 23. If B, U1, U2, up to UN is an orthogonal basis of a vector space V, we say that B is an orthonormal basis if all of the basis elements have norm 1. Now, an example of an orthonormal basis is the standard basis elements, E1 or I, J, K, which you've been using. These are the usual basis elements for 3-space, right? But of course there are other bases for 3-space. This one happens to be very nice because these vectors are orthogonal to one another and they all have norm 1. So that is an orthonormal basis for 3-space. Now here, notice there are 3 of these, so the dimension of the vector space 3-space is equal to 3. And that number is the same for any basis that I take for 3-space. Okay, just when you thought that this was very special, orthonormal bases are not unique. I could have a different orthonormal basis. For 3-space, let EJ be the n by 1 matrix whose entries are 0 if I is not equal to j, and that should say 1 if I is equal to j. And then B equals E1, E2, dot, 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 up to En is an orthonormal basis for Rn, in other words, n space. B is called the standard basis for Rn, and the dimension of it is n. Okay, example 10.5. Let M subscript 2, 3 be the vector space of all 2 by 3 matrices with real entries. And let this set B be that set. B is a basis for M2, 3. Okay, so in other words, I can obtain every element or every 2 by 3 matrix as a linear combination of these 6. And these 6 matrices treated as vectors are linearly independent. Now, how many are there? There are 6, so the dimension of this vector space is 6. Okay, let Pn of T be the vector space consisting of all polynomials of degree less than or equal to n. Let S be the set 1 t squared dot 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 up to Tn. Then S is a basis for this vector space of polynomials, and the dimension is n. So again, these polynomials are linearly independent. So if a0 plus a1t plus a2t squared and so on plus an tn is 0, then I must have a0, a1, all 0. Right? So these as vectors are linearly independent, and I can get every vector in this space as a linear combination of these. And so let's say that, and for all f of t belonging to Pn of t, there exists alpha 1, alpha 2, etc. up to alpha n, such that f n is equal to a sum of linear combinations involving the alpha. So I'm out of paper here, so I'll just put alpha 0 plus dot 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 plus alpha n t to the power of n. Okay, so hopefully you have a little bit more space to write that out in full. All right, let's move on to the next page. Example 10.7. Suppose we have u, v, and w in 3 space. Show that these 3 vectors form a basis for 3 space. Okay, so we want to show that they are linearly independent, and I can obtain all elements of 3 space as a linear combination or a unique linear combination of u, v, and w. Okay, so we set up an equation. So take an arbitrary element of R3, and let's give it a name, x equal to PQR, and put alpha u plus beta v plus gamma w equal to the vector x. So the question is, can we always solve for alpha, beta, gamma, satisfying this, and is the solution unique? So then, letting matrix A be the concatenation of u, v, and w, we have A times alpha, beta, gamma equal to the vector x. And so I can always solve for alpha, beta, gamma and get a unique solution if and only if A is invertible. So let's note that. We get unique alpha, beta, gamma in R3 if and only if A inverse exists. Okay, so all we really need to do is calculate the determinant of the matrix A. So let's do that. So we have 1 times 5375 minus 2 times 2335. I'm feeling deja vu here, like I've calculated this before. Then times 2537. Okay, and so let's have a look at what this is. 25 minus 21 is 4. This is 10 minus 9 is 1, so that's minus 2. This is 14 minus 15, so minus 1. Yes, I'm pretty sure this is familiar. So this is 4 minus 3 is 1, which is non-zero, so the inverse exists. And so the answer is yes. I can always solve this equation for alpha, beta, gamma, and I get a unique solution. So what we learn then is not only are these three vectors linearly independent, but I can obtain any element of R3 as a linear combination of those three vectors. All right, let's move on to theorem 29. Let V be a vector space of dimension n, and let S be a subset of V of m vectors where m is strictly greater than n. Then S is linearly dependent. Okay, so what we're going to do here is say let B1, B2, etc. up to Bn be a basis for the vector space V. Since it's of dimension n, I have n of them, exactly n of them. Okay, now suppose alpha 1 V1 plus alpha 2 V2, etc. plus alpha n Vn plus alpha n plus 1 Vn plus 1, and so on up to alpha m Vm is the zero vector. Now I'm just abbreviating this, so it's a very loose argument here. Now so we can always find, so A11 B1 plus, or I can always find the coefficients. So A12 B2 and so on. A1n Bn equal to V1 and so on. And so that is what forces all of the alpha to not necessarily be equal to 0. So this forces alpha 1 to alpha m to not all be 0. Okay, so this again is just an abbreviation of a full argument. Okay, theorem 30. Let V be a vector space of dimension n and S be a subset of V of n linearly independent vectors. Then S is a basis of V. So if we have a vector space of dimension n and n linearly independent vectors, then it's necessarily a basis. Okay, have a look at example 10.7. We have a vector space of dimension 3, and we have 3 linearly independent vectors, so it's necessarily a basis by this theorem. Theorem 31. Let V be a vector space of dimension n. If the span of those vectors is all of V, then V1 through Vn is a basis. And really this comes down to the determinant of the matrix A that's formed by the concatenation of these. Being invertible. Okay? All right, theorem 32. Let V be a vector space of finite dimension n, and let S be the set of vectors u1 through un, be linearly independent in V. Then S can be extended to a basis B of V so that S is a subset of B. Okay, so let's say this is M. Right, it was cut off, so let's assume that that was M, with M strictly less than N. If these are independent, then I can find another bunch of vectors to include as basis elements to make this into a basis. So let's say that we can make S into a basis for V by including more particular vectors. Right, because remember the entire collection of n of them have to be linearly independent. So that's why I say particular here. All right, moving on. Theorem 33. Let W be a subspace of an n-dimensional vector space V. Then the dimension of W is less than or equal to n. Right, so you can think of 3 space, for example. If you have a subspace of 3 space, say a collection of vectors that are all parallel to a plane, a given plane in 3 space. All right, so you try to visualize this now. Then the dimension of those vectors parallel to the plane has to be dimension 2, which is less than or equal to 3, right? Okay, example 10.8. Let W be a subspace of 3 space. If the dimension of W is 0, then W has to be the trivial vector space. If the dimension of W is 1, then W is a line through the origin. If the dimension of W is 2, then W is a plane through the origin. In other words, what I've been speaking of, though. So if you have a vector space in 3 space that has dimension 2, then the vectors in that have to be necessarily parallel to a given plane. Okay, definitions, rank and null space. We've been talking about null space. but let's say a little bit more. The rank of a matrix A, denoted rank of A, is the dimension of the vector space spanned by the columns of A. Okay, so the set of all linear combinations of the columns, or the number of vectors formed by the linear combination of the columns. The number of non-zero rows in the row-reduced echelon form. So this is the number of non-zero rows in the row-reduced echelon form. Now I should really go back to one of the row-reduced echelon forms that we had before. Oh, well, look, we have an example in front of us, right? So this matrix that I'm highlighting here on the left is an example of a row-reduced echelon form. So how many non-zero rows do we have? All right, so let's write this down here as an example. 1, 0, 3 over 2, 0, 0, 1, 5 over 2, 0, and 0, 0, 0, 0. So for example, this has 2 non-zero rows, and it's in row-reduced echelon form. So the rank of the matrix, let's come down here, so rank of the matrix 1, 1, 4, 0, 1, 3, 9, 0, 0, 2, 5, 0 is 2. All right, and this is also the vector space spanned by the columns, these columns here, or the dimension. So equal to the dimension of span of the vectors 1, 1, 0, 1, 3, 2, 4, 9, 5. Putting commas in here, and I don't have a lot of space. And 0, 0, 0. Okay, so the dimension that these four vectors spans is 2, is a two-dimensional vector space. Because these first three are going to be linearly dependent. Okay. The null space of an M by N matrix A with entries in K, denoted NS of A, is the vector space consisting of the vectors X in V such that A times X is equal to the 0 vector. Okay. So now, for example, so let's write it again, e.g., referring to this. So the null space of the matrix 1, 1, 4, 1, 3, 9, 0, 2, 5 is equal to the set of all vectors X. So it's X such that 1, 1, 4, 1, 3, 9, 0, 2, 5 is equal to the 0 vector. Right, and we can see from the row-reduced echelon form of this matrix how we should parameterize the set of vectors in this null space. Right, the null space is a subspace of V. Okay, so let's find this now from the row-reduced echelon form of A, namely 1, 0, 3 halves, 0, or augmenting that with a 0 vector, okay? 0, 1, 5 over 2, 0, and then a row of zeros. We have x equal to, say, alpha, beta, gamma satisfies alpha plus 3/2 gamma is 0, beta plus 5 over 2 gamma is 0. And so then we can write alpha, beta, gamma, which is x, as minus 3 over 2, minus 5 over 2, and 1 multiplied by gamma. Now we treat gamma as a parameter, and so the vector space, so the null space of the matrix A, is spanned by some linear combination of this, but there's only one. So let's just tidy this up now and choose the vector 3, 5, minus 2. So I've just taken this vector right here next to the gamma and multiplied it by minus 2 to get this one, because it looks more attractive than this, in my opinion. But beauty is in the eye of the beholder, right? Okay, so we found the null space of this particular matrix here, and it's got dimension 1. So the dimension of the null space of A is equal to 1, and this is called the nullity of the matrix A. All right, so we should probably write this here. Dimension of the null space of A is the nullity. Okay, let's move on to the next page. The Wronskian matrix. Okay, so you can see page 155 of the reference 4 for this. Definition 27. Let f, a, b be the vector space of functions defined on the interval from a to b. Define the Wronskian function, uppercase W, to be the determinant of this matrix involving the derivatives of these functions, where f superscript m of x denotes the mth derivative of the function f of x with respect to x. Okay, let f1, f2 up to fn be in this vector space of functions if there exists a point x0 in the interval from a to b such that the Wronskian at x0 is non-zero, then these functions are linearly independent functions in that function space. Show that e to the x and e to the minus x are linearly independent in the function space over the interval minus infinite to infinite. So we want to form our Wronskian matrix for this, but since we only have two functions, it's going to be 2 by 2. So let f1 of x be equal to e to the x, and f2 of x be equal to e to the minus x. Okay, then our Wronskian of f1 and f2 as a function of x is the determinant of the 2 by 2 matrix f1, f2, f1 dash, f2 dash. So determinant of e to the x, e to the minus x, okay, so this is at x0, and so here I've got to somehow denote that I'm, say, sub in. All right, so I'm just going to put a round bracket x subscript 0, but you could put another vertical line and at the bottom write x equals x0 if you like. That would be another notation for that. Okay, so then the derivative of this function is e to the x, and the derivative of e to the minus x is minus e to the minus x. Okay, so let's take the determinant of this. So we have minus e to the x times e to the minus x, and then subtract the product of these two. Evaluated at x equal to x0. Okay, let's simplify this. So we have minus, now the product of these is e to the sum of x and minus x, which is 0, so e to the 0. And then again, minus e to the 0, evaluated at x equals x0. Okay, so this is minus 1, so minus 2. And notice this is not equal to 0, so what can we conclude? So by theorem 35, e to the x and e to the minus x are linearly independent, and I'm going to abbreviate that Li in the function space minus infinite, infinite. So on the real numbers essentially. All right,